Welcome to this new video. So in this video we are going to finish chapter 2. So we'll cover section 2.4 about sequences defined by induction, or sequences defined recursively, or sequences defined by a recursive formula, if you like. So actually we already encountered such sequence in the appendix C of chapter 1. Okay, so it was a sequence of the form u0 is given and un plus 1 is a function of un. So the next state, if you like, so the state 0 is given and we start in induction. So if we know u0, we know u1. If we know u1, we know u2, and so on. So the next state is a function of the previous state. Okay. Now, the function f is also called a discrete dynamical system, and the sequence un is called the orbit of the dynamical system. So if you think, you can think of this sequence as the sequence of iterates of u0. So it's u0, f of u0, f of u0, and so on. So this is the orbit starting from u0. Now, this is a dynamical system, and so you can see it as a map, actually, that takes a point into a sequence. So to each starting point, there is a sequence of successive iterates of this initial point. Now, the behavior of such orbits may be complicated. It's not always easy. So we saw actually in appendix C of chapter 1, we had the case of convergence to a limit, right? So we may have convergence to a limit. We may have convergence to plus infinity. Okay, so we say conversion to plus infinity in the sense that limit of un is equal to plus infinity or minus infinity. We may say divergence to plus infinity, but this is different from the case of divergence. So here in this case, un is unbounded. Okay. We may have oscillation. So the sequence need not converge to a limit. It may oscillate between 2 or 3 or 4 or more limits, actually. And finally, you may have what is called a chaotic behavior. So chaos is a possibility, actually, and it was discovered actually in the 50s or 60s when people started working on computers. Actually, with the advent of computers, as you shall see now, we can represent such sequences. Actually, we can follow them graphically, as we shall see now. Okay, so we'll get to chaotic behavior. So, but let us illustrate these behaviors actually with examples. Okay, here we have the function f of x equal 1 plus radical x. It's in green. And I drew the first bisector y equal x in white. And note that the two graphs meet at a certain point, which is a fixed point of x. So it satisfies the equation x equal f of x. And we can actually find it. It's not difficult. So it satisfies the equation 1 plus radical x equal x. If you solve it, you find two solutions. One is less than 1, so actually it's rejected. And the other one is 3 plus radical 5 over 2. So maybe you can pause the video and check that this point is actually has coordinates 3 plus radical 5 over 2. Okay? So it's about 2.618. Now, let us start with an initial value, for example, u0 equals 0.3. Okay, so how to find or represent successively the iterates of u sub 0? Well, if u0 is here, f of u0 is on the graph, actually. So I draw a vertical line from u0 that touches the graph at a point whose ordinate is u1. So this point here has coordinates u0, u1, because this is the image of u sub 0. So u1 is here. If you want to represent u1 on the x-axis, because everything happens on the x-axis. So where is u1 on the x-axis? I draw a horizontal line and I stop when it touches the first bisector. And then I draw a vertical line. So this is u1. So you have two symmetric points, u1 here. So this is u1 in the plane, it's u1, 0, and this is 0, u1. So if u1 on the y-axis is here, then u1 on the x-axis is here. So if this is u0, this is u1. And now I repeat the procedure. I find the second iterate, u2, so f of u1. So f of u1, same procedure, I get u2, it's here, and so on. u3, u4, yeah. So u2, u0, u1, u3, okay? So, and if you continue, we see that the sequence is increasing, right? And it appears, it seems to converge to some limit. And indeed, this is the case. The limit being the fixed point or a fixed point of f. Okay, so L here, as you may check, is 3 plus radical 5 over 2. So this is the simplest behavior of conversion to a limit or to a fixed point. Of course, we may have a sequence converging to the limit point from above. So we could have a decreasing sequence if you started, for example, with an initial state bigger than L. Try to do that actually. See what happens if u0 is bigger than L. For example, u0 equal 3. What happens? So this is the first behavior. Now, another behavior is also converged to a fixed point, but we have a small oscillations here. So I took here f of x equal cosine in green. It's decreasing. Of course, I'm working on 0, 1 here. And I start with u0 equals 0, 2, and I repeat this construction. Okay? And by the way, such figures are called the cobweb of the dynamical system. Here, the situation is a little bit different. We still have convergence to a fixed point, right? Same here, L. It's the solution of the equation cosine x equal x for x in between 0 and 1. But here we have small oscillations. So u0 is here, u1 is on the right of L, u2 is on the left, u3 on the right. So we have oscillations, smaller and smaller oscillations until we reach the fixed point. So this is another example of convergence to a fixed point. Now, we may have divergence or convergence to infinity. For example, it's easy to give examples. For example, I took here f of x equal x plus 1. And you can start with any value. I took 0.7. And if I do the iterations, actually, we see that u0 is increasing and unbounded. So it converges to plus infinity. And it's easy to construct an example where un converges to minus infinity. Okay, this case is not very interesting, actually. More complex behavior. I took here f of x equal 3.2 times x times 1 minus x, okay, which is a parabola which vanishes at x equals 0 and x equal 1. And this is the first bisector in white. So we have two fixed points actually. Here's 0 and that point that we can compute actually. It's not difficult. We have a formula because a fixed point of, if you solve the equation f of x equal x, we get a second order polynomial equation. So we have two roots. This was not the case with cosine because we don't have a formula for the solution of cosine x equal x. Okay, so let us start here with, for example, 0.15, and let us follow the orbit, right? So here, because it's the behavior is a little bit more complicated, I didn't wrote because there's no place for. So this is u0 here, this is u1, u2, u3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We seem here, what do we have? We don't have convergence, but we have what we call a periodic behavior. So we have an oscillation between two limit points. One is about here and the other here. So the sequence or the orbit will oscillate all the time. So we may say that it's a kind of convergence. Yes, it's convergence, but not to a fixed point. It's convergence to a periodic orbit. Okay? An orbit consisting of 2 points, right? Now, more complicated, I increased the parameters, so the same shape, but I increased a little bit the coefficient from 3.2 to 3.5. And I started from the same point, and look what happens here. What do you observe? We have here also a periodic behavior, but it's an orbit of period 4. So we have 4 limit points. 1, 2, 3, 4. So we have a double cycle, if you like. So the sequence will oscillate around 4 points, 4 distinct points. And this is what we call an orbit of period 4. If we continue to increase this parameter, we may get orbits of period 8, and then periods of orbit 16, and so on. I will not do it. But now let me give you something even still more stranger. So I will take 4x 1 minus x. Okay, the maximum is at 1 here. And let us see. So let us count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. I stopped at 21. I represented here the initial point by a red dot. So this is the initial point, and this is the 29th iterate. After 29 iteration, we arrive at this green point here. So what do you observe here? We don't have convergence, neither to a fixed point nor to a periodic orbit. And the orbit of U0 seems to wander chaotically in the interval 0, 1. So there's no pattern here. And there's something actually that I want to show you is that if we change a little bit the initial condition, what happens? Let us start with 0.14 instead of 0.13. So now we are almost very close to our previous example, and let us count what happens. Let us see what happens. So it's a different behavior. It's a different orbit, not the same thing. So, and look what happens. After 29 iteration, we are again close to the initial point. So this is what we call sensitive dependence on initial conditions. And this is one of the signatures, one of the features of chaos. So a small perturbation, a small error in the initial condition can lead to great errors after enough iterations. And this makes these systems unpredictable. So in theory, these are what we call a deterministic system. So if you know U0, we know U1. If you know U1, we know U2. So in principle, we know all the orbit. But a slight perturbation on the initial condition will lead to something different. So this makes impossible the prediction of the behavior. okay, in the long run. And so this, I wanted to illustrate this. Just to tell you that sequences defined by induction or by or recursively can be very complicated, okay, even in one dimension. Now, you study such things actually usually in a course about discrete dynamical systems or a course on chaos. Unfortunately, you don't have such a course here, but there are many online resources where you can learn more about this topic actually, which is fascinating. Now, in the remainder of this course, we are not going to talk about chaos, neither about periodic behavior. We are just going to say something about convergence to a fixed point, which is the simplest possible behavior of dynamical systems. And if you like the subject, actually, I invite you to write a Python code to draw such graphs, such cobweb graphs, okay? And try to experiment with changing the parameter here or changing the initial condition and see what happens. Actually, even in this case, you may still have periodic orbits, actually. So not all orbits are chaotic, actually. But for some initial conditions, so some orbits are chaotic, some other orbits are periodic, actually, or converge to a periodic orbit. Okay, so try to experiment with such system if you have time. It's very instructive. Okay, and now we go back to the course. So we'll present few results about convergence to a fixed point. Okay, so first result, consider a continuous function f from an interval of r into r, and consider a sequence defined by this formula, by recurrence or by induction. So the initial point is not specified here. If this sequence is convergent to a limit, if it's convergent, it need not be convergent because we saw some examples where it's not convergent. But if it is convergent to a limit, then necessarily this limit is a fixed point of f. So it satisfies the equation f of L equal L. So graphically, it's the point. It's the abscissa of the point where the graph of f meets the first bisector. Okay, now here, of course, I'm assuming that you already know what continuity means, at least in terms of sequences, but we shall go back later to the problem of continuity in the next chapter. So one definition of continuity at a point L is that if un converges to L, then f of un also converges to f of L, right? This is continuity. But f of un is un plus 1. So un plus 1 converges to f of L. But if un converges to L, then un plus 1 also converges to L. So we have two limits here. By uniqueness of limits, we must have L equal f of L. So this is very easy. So if I give you a sequence defined by induction in this way and tell you to study the behavior to see if it's convergent or not, then where do you seek limits? You seek the limits in the fixed point, among the fixed point of f. Okay? And we shall see some examples in the exercises, actually, that I will post as soon as possible, and I will correct them next week. Now, second result, suppose that f is increasing, not necessarily continuous. Then we have two cases. If the first term or the next term is bigger than, so if u0 is less or equal than u1, then the whole sequence is increasing, not necessarily strictly. Okay, so we should say non-decreasing. So, and otherwise, if u0 is bigger or equal than u1, then un is decreasing. Okay, this is very easy. This just follows from the definition of increasing function. If u0 is less or equal than u1 and f is increasing, then by definition f of u0 is less or equal than f of u1. right? So we prove that by induction. It's enough to prove that un plus 1 is less or equal than un, right? This is true for n equals 0 by our assumption, because we are in this case. So if now I apply, so suppose now it's true for some n, then since f is increasing, f of un plus 1 is less or equal than f of un. And what does this mean? F of un is un plus 1, and f of un plus 1 is un plus 2. So my proposition is true for n plus 1. And by the induction principle, it's true for every n. So the sequence is increasing. The other case is completely similar. Suppose that u0 is bigger or equal than u1. So we prove by induction the reverse inequality. The result is true for n equals 0 because by our assumption, and so we suppose that it's true for some integer n. So, and we apply f. And we get un plus 2 is bigger or equal than un plus 1. So the result is true for n plus 1. And therefore, by the induction principle, un plus 1 is bigger or equal than un, and therefore un is decreasing. Okay, so everything depends on the initial two conditions. Okay. Next result, same thing, but here we assume that yeah, I forgot to put continuous here. So consider now, so pay attention to the assumptions. First thing, we have f continuous. Please add that. It's from AB to AB. It takes AB into itself. This is important. I will tell you why. And third assumption, it's increasing. Now, if you start in the interval AB initially and you iterate, then un is convergent, and of course to a fixed point, because by a previous result, we know that the limit is necessarily a fixed point of f. Now, by the previous proposition, 2.3, un is monotone. So it's either increasing or decreasing depending on the position of u0 and u1. Okay. Now, since f, the domain of f is AB, this means that you can prove by induction that necessarily un is an AB, because u0 is an AB, f of u0 is an AB, f of u0 is an AB. So by induction, the sequence is between A and B, which means that it's bounded from above and from below. Since it's monotone, then it's convergent. So if it's increasing, it's bounded from below by B, so it's convergent. If it's decreasing, it's bounded from below by A, and therefore it's convergent. So in both cases, it's convergent in a monotone way. Okay? And that's it. So please add the assumption of continuity here. Actually, I need the assumption of continuity to prove that it's convergent to a fixed point. But if you just need to prove that un is convergent, you don't need the assumption of continuity, right? Okay. But to add this, you need right. In order to apply 2.2, we need the continuity of f, because otherwise you can give counterexamples. Now I have a remark here. If f is just continuous from AB to itself, it's important to have this assumption. Then f has at least one fixed point. And now we have two cases. If f is increasing, then the fixed point need not be unique. So we shall give actually examples. Actually, we did already give an example of 1 plus radical x had two, well, yeah. So, and in the exercises, we shall explore these cases. So if f is continuous, so the graph of f may intersect the first bisector in several points, actually. So you may draw a figure if you like. However, if f is decreasing, then the fixed point is unique necessarily. Cannot have more than one fixed point. Why? Actually, this is also clear from the figure. If you try to draw a figure, try to draw the graph of a continuous decreasing function, if it cuts the first bisector, it cannot cut it in more than one point, because otherwise it would be increasing in some intervals. So this is impossible. Now, why is it so? So we have actually two things to prove. First, why any continuous function has a fixed point from AB to AB? Why? This is actually a consequence of a result that maybe you know from high school. It's called the intermediate value theorem, that we shall prove next in the next chapter and next year as well, in a more general context, because it's a topological result. So if f is continuous from AB to itself, consider the function g of x equal f of x minus x. Then first, g is continuous. And second, g of a is f of a minus a. And this is something bigger or equal than 0 because f takes value in AB. So f of x is bigger than or equal than a for every x, not just a. In particular, f of a is bigger or equal than a. So g of a is positive, is bigger or equal than 0. And for the same reason, f of b is less. This is 0 actually, sorry. So f of b is less or equal than b. So f of b minus b is less than 0. So this is 0. So what do we have? We have a continuous function taking initially a non-negative value and finally a non-positive value, right? So a continuous function goes from a positive or non-negative value to a negative value, so it must vanish. This is the content of the intermediate value theorem, right? So, sorry, this is 0 instead of b. And now, if g vanishes at some point L, then necessarily f of L equal L. So f has always a fixed point if it maps AB to itself, a closed interval AB into itself. And now, as an exercise, try to construct an example of a continuous increasing function having more than one fixed point. Okay? Now, let us consider the case where f is decreasing. Why the fixed point is unique? Because we reason by contradiction. Suppose that f has two fixed points. One is L, one is L prime. So we may assume that L is less than L prime because we can relabel them, if you like. So call L the smallest one, because they are distinct. One is less than the other. Call the smallest one L and the other L prime. Since f is decreasing, then f changes the order. So f of L is bigger or equal than L prime, right? Because it's decreasing, right? Not necessarily strictly, but it's okay. And this is a contradiction. Why? Because L is a fixed point, so f of L equal L, and therefore L is bigger or equal than L prime. But I assume that L is less than L prime, so we have a contradiction. Okay, therefore the fixed point of f is unique if in the case of a decreasing function. And now, last result. What about a continuous decreasing function and a dynamical system associated with it? In the decreasing case, unlike the increasing case, we don't necessarily have convergence, but we have convergence of two subsequences. So pay attention to the difference between the increasing case and the decreasing case. The subsequence u to n is convergent, of course, to a limit which is a fixed point of f of f, circle f. And the sequence u sub 2n plus 1 is convergent to another limit, which is a fixed point also of f circle f. Now, it's possible that L equal L prime, but it's not necessarily the case. It's possible that u sub 2n converges to a limit, and u sub 2n plus 1 converges to another limit. And I'll try to give you an example in the exercises. So, yeah, now this is just a consequence of the previous proposition. Why? Because if f is decreasing, then f composed with itself is increasing, as you may check, because I reversed the order twice. And also, if f maps AB into AB, then f of f also maps AB into itself. Therefore, I apply the previous proposition to not to f, but to f of f. So let me consider two sequences. Vn, I denote them by the same symbol, but actually could call them V and W. So consider the first sequence V having the same initial condition as U, so V0 equal U0, and Vn plus 1, Vn is associated to the dynamical system f of f. What's this sequence actually? So V0 equal U0, therefore V1 equal f of V0 of U0, which is U2. So V1 equal U2. And V2 is U4 and so on. So this is just the sequence U sub to n. And if you start with U1 and you do the same iteration, we get the sequence U to n plus 1. So if you start with 1, okay, what is V1 here? So we put n equals 0. So V1 is f of U1. So it's U3. So U1, U3, U5, etc. Now, by proposition 2.4, both such sequences are convergent in a monotonic way to a fixed point of f of f. Now, here f has a unique fixed point because it's decreasing, but f of f may have more than one fixed point. So I cannot say that L equal L prime. Now, if f of f has a unique fixed point, then necessarily the two limits are equal. Okay. And so this concludes this video and chapter 2. So as I told you, I will post the exercise as soon as possible, and I will correct them next week. So thank you for your attention, and I hope that I convinced you that mathematics can be fun. It's not an austere discipline. You may have fun, and you may experiment with things, especially with the aid of computers, which are very necessary actually for modern mathematicians. Every modern mathematician should know at least one programming language and should know, I suggest Python actually and LaTeX. So thank you for your attention and see you next time.